Independence worked example. You and your friends are going to the cinema. You'll buy a grape slushy with a probability of 0.6, caramel popcorn with a probability of 0.4, or both with a probability of 0.24. There is a 0.24 chance of you not buying anything. Are the events buying popcorn and buying a grape slushy independent? So let's start by representing this scenario in a Venn diagram. But firstly, let's write the notations we're going to make use of. So we're going to let S be the event that we buy a slushy. So let S represent the event that we buy a slushy. Then we will let P be the event that we buy popcorn. So when we draw a Venn diagram, let's start off with our sample space, which we will denote with omega. And then we will have all the events S and the event P. So here is S for the scenarios where we bought a slushy, P for the scenarios where we buy popcorn. And this area where they are overlapping, this is our intersection. This area over here, this is S's intersection with P. So we're told that the intersection of S and P, the probability that we buy a slushy and a popcorn is 0.24. We're also told that there's a 0.24 chance that we don't buy anything from this information over here. So 0.24 chance of buying a slushy, 0.24 chance of buying nothing. There's a 0.6 chance that we buy a slushy, and there's a 0.4 chance that we buy popcorn. So we have a 0.6 over here, which represents this entire S over here, this entire circle of the S, and we have a 0.4, which represents the entire P. So, but we are double counting because we have the intersection over here. So we're going to need to say 0.6 minus 0.24 and 0.4 minus 0.24 to get the probability of, for the left-hand side, this is the probability of S, this intersection with everything that is not P, so P complement. So this is S's intersection with everything that is not P. That's what we want on the left-hand side, and that is equal to 0.6 minus 0.24, which is equal to 0.36. Then we want the probability of P intersecting with everything that is not S. So we just want this, you can think of it sort of like as a chunk of the moon, as the moon with a chunk removed. So we just want the P's intersection with everything that's not S. And that is equal to 0.4 minus 0.24, which is again equal to 0.16. So now we have these probabilities. So the probability that we can write down here is 0.36, and the probability we can write down here is 0.16. So now we've represented this information in a Venn diagram. Let's make sure that all our numbers add up to 1, because this is the entire sample space. All the events have to add up to 1. So we have 0.36 plus 0.24 plus 0.16 plus 0.24. This is the probability of the sample space. This is probability of all the things occurring. So 0.36 plus 0.24 plus 0.16 plus 0.24, all of this adds up nicely to 1. So we are verifying that everything is accounted for, there's nothing strange here. So now that we've represented all of the information correctly using a Venn diagram, let's get to the underlying question. Are the events buying popcorn and buying a grape slushy independent? Well, what do we mean by independent? And we should recall that the independence for events A and B, and if events A and B are independent if and only if the probability of A's intersection with B can be written as the probability of A multiplied by the probability of B. So only if we can write the intersection as a product of the individual events' probabilities can we say that these two events are independent. Then A and B will be independent. So in our case, we have got the event S and the event P. So the probability of S intersection with P, probability that we buy a slushy and popcorn, is equal to 0.24, as we can see from the Venn diagram over here. So this is where our 0.24 comes from. The probability of S is equal to 0.6. The probability of P is equal to 0.4. So the product, which is the probability of S multiplied by the probability of P, is equal to 0.6 times 0.4, which is equal to 0.24. So yes, because the probability of S intersection with P is equal to the product of the probability of S and the probability of P, then we can say, yes, the events S and P are independent.